Hi, and welcome back to another easy LeetCode problem. You know the drill. Easy problems allow you to practice the interview process and don't distract you as much by drawing you into solving difficult problems. So this time we're going to look at LeetCode 3417, Zigzag Grid Traversal with Skip. And we're going to read the problem description first, check out the constraints, look at the examples, formulate our solution approach, maybe give some trade-offs and the runtime complexity early before we implement the first line of Python code. And after we've implemented the code, we step through it with a mental debugger to spot any issues. And then we shall run the tests and finally make the submission to see if LeetCode accepts our solution as well. So let's get right into it. Let's zigzag. You're given an m by n two-dimensional array, a grid, of positive integers. Your task is to traverse the grid in zigzag pattern while skipping every alternate cell. Okay. Zigzag pattern traversal is defined as the following below actions. Start at the top left cell. So the top left cell. Move right within a row until the end of the row is reached. Drop down to the next row, then traverse left until you reach the beginning of the row. Continue alternating between right and left traversal until every row has been traversed. Note that you must skip every alternate cell during the traversal. Return an array of integers result containing in traversal order, the value of the cells visited during the zigzag traversal skip. All right. So the size of our grid is limited. Now for the runtime and space complexity analysis that we will be doing, we always assume that it's not limited. It's only limited here because LeetCode needs to be able to run our code in a reasonable amount of time. But in an interview, you need to be able to explain asymptotic runtime, and then you assume that there's no limit. And so yes, so this is the height of the grid. N is the height, and M is the width of the grid. And then we have the grid cells. They have values between 0 and 2500. We don't really care that much about it because we just need to return them. We don't need to do anything with those values besides logging them. So, okay. Example 1, grid. So this is a 2x2 grid. And we have to skip every alternate cell. So we start at position 0, 0, that's the 1. We go one step to the right. We go one step down. So this will be the second position after skipping, the third position, and we skip the second one. So we add 1 and 4, and then we go to the 3 and down, but then we're outside of the grid, so there's nothing to do here. So the output is 4 and 1. Next example, same thing, except that now there is a third row, so we have to add that as well. And then we do the stepping continue. I think that's self-explanatory. And finally, example 3, it's the same thing, right? We skip every second cell. Okay, cool. So yes, I think what we can do, we could just go for a solution. It's obvious that we need to iterate over all of these elements. And the skip step is fixed, right? It's size 2. So if we visit every single element or if we skip every element, doesn't really matter. What matters is that we only log every second element, but we can step through every element without changing the runtime complexity of our solution or the space complexity. So I think the runtime complexity will be, if we traverse all of the cells, will be simply n by n times m. And the space complexity will be the same, even though, no, it will be the same, because that's how many elements we're going to see in the output. So yeah, so we will do exactly that. And so the runtime complexity is n by n, time and space as well. What did they say here? N is the height. M is the width of the grid. And, you know, you could also say that the runtime collapses n into space as well. But then you'd have to say that n is height times width of the grid, right? So you can give different, like if somebody says, oh, I have a linear time solution. Well, it's linear in the number of cells on the grid. But if you break it up by width and height of the grid, then it's a product of those two. Anyways, I'm getting distracted. Okay, cool. So now what we will do, we will have a position. And we start at the top left, right? That's what it said. Start at the top left cell. That's where we're starting. And we're now going to iterate over all of the values. And let me just think for a second. You know, there's a way of how you can iterate through these two-dimensional grids. One is by having, well, two positional, two coordinates, like x and y. And the other one is just by index. So you could say this is index 0, 1, 2, 3, 4, 5, 6, 7, 8. And I was just thinking, you know, how do we do this? If we do the indexing one, then we have to deal with the fact that every second row is going to be reverse order. That's going to be annoying. So that's why I'm going to choose the px, py coordinates for the indexing. So, but when do we stop? So what I would suggest is we stop. Let me just get the width and the height real quick. And the height is length of grid of the first row is the width. And the length of the grid is the height. So what we do is, if our position, well, if our y position moves out of the height, then we should be done. And remember, we're zero index, that's why we have the equals and not the larger. And of course, we're going to stay inside while our y position is smaller than the height. Once we step into a row that doesn't exist, we know we're basically done. And this is where we have to do the work. But we also have to return a result, right? And the result will be an array containing our integers in traversal order. So we just set the result as well. And then at the end, we're going to return the result. Cool. So now what do we do? Well, the first thing is we assume that we're stepping through the grid. So let's just implement stepping through the grid for now. And then we'll deal in the second step with adding items to our result or not, yeah. So what we'll do in every move is, so we get the value of the current cell. So that's at py, px, and then we will do the next step. So what we do is px, we do another step. There you go. Let me see. Oh, what we could also do is we could actually, what we could do is we could increase the step by 2 right away. And we just check if we are over the boundary. We just add the value of the width to it, and we will all, oh no, we can't do that. Sorry, we can't do that. Yeah, I'm thinking again, because we need to determine in which row are we currently, right? So we need to keep track of the row. So the value is at the position. Now, if py is an even row, that means we're going left to right, right? So in that case, we're going to increase our px by 1. Otherwise, we're going to decrease our px by -1, correct? Now, we have to check if px is still within the boundaries. If px goes beyond the limit of the row, or when it's going backwards, it goes below 0, that knows we need to increase our y position. So if px is larger or equal to the width, in that case, we set px, so we take px one step back. It's like stepping from 3 to this cell that doesn't exist. So we do one step back, but we also do a step down. And that is py plus equals 1. Similarly, if we if px goes below 0, that means we have to take a step back to get back into bounds. And we have to increase our py as well. Right, so now we're actually doing the stepping through the grid one by one. And every time the value, value will assume all of the values that exist in the grid. So now how do we skip every second one? Well, let's just think about this real quick. So we could keep track with an index that just is either 0 or 1, that just keeps alternating. That's something we could do. That would probably be the easiest one. And we could call this parity. And every step, we're going to increase the parity by 1. And we do modulus 2. And if parity is equal to 0, we're going to append the value to our result. So that's something we could do. There's probably something smarter we could do as well. Just look at, the index position of the x and y, but we don't really need to do that. Right. So yes, and I think that is an entire solution. It's not yet that beautiful, I think, but I think it should work. So let's just step through it with our mental debugger real quick. In this example, we determine the width and the height. So it will be 2 and 2. So what we will do now is we will set our initial position to 0, parity is 0. We go into our loop because py is 0, which is smaller than 2. So we're good to go to keep entering the while loop. We get the value 1. The parity is 0, so we append 1 to our output. Oh, and I just see here, we're only adding the white cell. So what we have to do here is basically just change it to 1. So because the parity is 0, we're not actually adding it, but we're going to increase the parity for the next round, right? Where we do that doesn't matter, because we're not going to use parity until the next iteration. Right, cool. So now we check if py equals 0, which is true. We increase the x, so x goes to the next position. That's it. X is not larger or smaller than the boundary allows. So we go into the next loop. Py hasn't changed, so now the value is 2. But now the parity is 1, so we're adding... I made a mistake. I looked here, but I should have looked here. So that was actually correct where it's 0. So we added the 1. Now we're at position 2. We're not adding it because the parity is 1. Doesn't matter. So next step, we increase our px by 1. So that means now px is pointing at position 2, which is out of bounds. So this case happens. So px steps back. So px goes back to 1, but py gets increased by 1. Yeah. So I think that's good. Let's just run it. I've been rambling for far too long anyways. So, okay. So there are no syntax errors so far. And for the example case, it seems to work quite well. And yeah, let's submit this, see what happens. There you go. So that's a solution. And as always, good practice is to just look at somebody else's solution. Maybe they have a way that's even better. Let's see at this. Let's look at this one. So this has the same time complexity. By the way, n divided by 2 space complexity. That's the same as n space complexity. You don't really need that. And it's also incorrect. Why would it only be dependent on the height of the grid? Space complexity. Height over 2. So that is, I think, incorrect. Yeah, so let's not bother with that one. 2 lines of code. Let's have a look at this. So this is actually iterating over all of the rows. So it chooses step size 2. Then it reverses the row. I don't remember if in Python actually reverses it or if it just adds a flag to that array. So I don't know if it actually performs the reversal or if it gives you like an iterator that just iterates in reverse order. I don't know. I should probably look that up. Because if you can explain that, oh, this actually is not an O of n operation, you know, that's bonus points. And then it returns a list of the chain of, okay, for row and grid. So this actually reverses the row. Oh, I see. So what it does here is it takes every second row and reverses every second row in the array in this grid. So that means it can then just iterate over all of the rows because they're already in the correct order and extract the elements from them with a step size of 2. Yeah, this person also not sure about this. I think this is the same space and time complexity. You're iterating over n rows and you're reversing m elements in every second row. Yeah, it's the same. So there's no optimization. And I mean, kind of, I don't know. For an interview, this is going to be a nightmare to explain unless the interviewer knows Python. Not every interviewer knows the programming language that we are interviewing in. So yeah, probably something that you don't really need, but it's nice to look at these examples and learn a little bit from their code as well. So that's pretty much it. I don't really like these, that doesn't really look beautiful, but it works, which is, I suppose, the main thing. Yeah. But yeah, I hope you found that interesting. Try to implement it yourself. Maybe you come up with a nicer solution than this.